Hello people, in this video I'm going to talk about a sigma algebra. So a sigma algebra is, the idea behind the sigma algebra is that you want a space within which you can define the events. Because usually when you have an experiment and you're trying to calculate probabilities about it, you have this set of outcomes. Like the set of outcomes could be like, heads or tails or numbers on the face of a die that was rolled, but the events aren't defined in that way. The events are defined like, what's the probability of having an odd number pop up on the dice, or if you're throwing a few dice, what's the probability that the number be at least 10? So the whole purpose of the sigma algebra is to really define a space where those events can live in a formal way. So that's the purpose of it. It's centered around the events, which you're going to speak about and try to calculate probabilities about later on. But right now I'm just going to talk about the definition of a sigma algebra, and we'll go from there. Okay, so the first rule of sigma algebras is the empty set is an element of the sigma algebra. The second rule of sigma algebras is that if you have E, which is a set in a sigma algebra, then its complement in S is also part of the sigma algebra. Now, if we take 1 and 2, this gives us that S is necessarily in the sigma algebra, since S is equal to, let's say, the complement of the empty set in S. Okay, so if you have the empty set, and what's not in the empty set? Well, everything. So obviously, S is going to be in the sigma algebra in this case. Now, the third definition is that if we have a countably infinite number of sets which are in the sigma algebra, then their infinite union is also in the sigma algebra. The reason why we need infinity here usually is because, we're developing a mathematical framework to calculate probabilities, and some distributions have an infinite range, or an infinite domain. So even though everything in the real world is not infinite, like you can't have infinite dollars in your bank account, some people do have quite a bit of money, and if you were to plot a distribution which plotted, like, let's say, distribution of wealth, you could allow for the hypothetical infinite amount of wealth, even though the probability of it occurring in your model is so small, it's not meaningful. So that's essentially the reason why we have to deal with infinities, is because some of our models have infinity cooked up into them. So essentially that's kind of where we're going with that. Now, if you take 2 and 3, as well as the rules for set theory, specifically De Morgan's laws, you'd be able to prove, and you can do this as an exercise, that the infinite intersection is also in the sigma algebra. So this is not a definition, this is actually a consequence of the definitions listed above, as well as the axioms for set theory. So the thing that I haven't talked about is what is a power set, because I've said here that the sigma algebra, sigma in the power set on a set S, is a collection of subsets. So if we're going to say something, we should actually, define what it is that we're saying, because otherwise you could say anything. Sigma in googly gack doesn't mean anything. So what is the power set? Power set is the set of all subsets of S. So for discrete sets, that's what the power set means. So so it's the set of every single subset that you could create. So let's say your S has, I don't know, 25 outcomes. Okay, you could create a whole bunch of subsets of those 25. Some of them could have 3 outcomes in them, 4 outcomes in them, 5 outcomes in them, 6 outcomes. All of those sets would be included in the power set. Okay, so I took a very, very simple example. And this example is a horrible final exam. So this horrible final exam is going to be an exam where you have 2 questions. They are true or false questions, and you either get it right or you don't. So the outcome on the exam is either 0, 50%, or 100%. So the only way to pass is to get them both right. So it's a scary final exam. So for this experiment, which is the final exam, you could think of it as an experiment, our sample space S is going to be this bad boy right here. Now I've taken the time to add the empty set there because the empty set in set theory is a member of every single set except itself, because it is empty. It's kind of silly, but the empty set is an element of any set, let's say E, except when E is equal to the empty set. Okay, so that's the case there. So here I'm going to, well, what's been written out is the power set of S. Okay, now what I haven't done is put the empty set in every single one of these, just because, right? So like the empty set could be included in every single one of these, but I'm not going to do that because it's a big waste of time. And so just understand that the empty set is inside of every single one of these sets. Now in this case, okay, so what I've done is I've enumerated them by the amount of elements inside of them. Okay, so I started with 0, and that's just the empty set. It's the only one. There's one of them, and that's the only one that has no outcomes in it. Okay, then the ones that have one outcome. So one outcome is basically one outcome. It's like a result on the exam. So you either get the first question right and the second one wrong, or you get them both right, or the first one wrong, the second one right, or you get snake eyes and you're not having a good day. Okay, so then you could look at, well, what are the ones that have 2 elements in them? And you have, all the possibilities. You've enumerated all the possibilities where there are 2, and there are 6 such possibilities. And here we have the ones with 3, and there are 4 possibilities that have 3 elements in them. Any other sets will either have duplicates or, like, I've listed them all. That's the power set. And 4, we only have 1 of them, and it's usually, there's 4 outcomes, but the set has like 5 members because the empty set is a member of it, but there's only 4 outcomes anyhow. So in essence, okay, so you get 1, 4, 6, 4, 1. That looks like something familiar. What is that? Well, if you remember the binomial coefficients, 1, and then it'd be 1, 4, 6, 4, 1. So if you remember that, you'll remember these are essentially the binomial coefficients, and then the sum of these lines usually is 2 to the n. And so for a set, for a set S, then the cardinality of the power set of S is equal to 2 to the n, where S is just n different outcomes. Okay, so it's rather big. So in this case, it looks like there's, let's see, 10 plus 5 plus 1, 21. That makes, no, that's not right. 10 plus 5 plus 1, 16. Okay, there's 16, so that's 2 to the 4. Okay, because we have 4 elements here. We've got 4 elements here, and 2 to the 4 is 2 times 2 to the 3, which is 4 times 2 to the 2, which is 8 times 2 to the 1, which is 16, which is just so happens to be the quantity of elements in the power set. Okay, so then, why is it, so how is it that this power set, and the sigma algebra, which is a subset of it, how is it that we define, how does this help us define our events? Well, okay, so let's look at this. E equals the number of correct, an odd number of correct answers. Well, that corresponds to specifically this set, because you either got the first right and the second one wrong, or you got the first wrong and the second one right, because any other answer would be even, and also the complement of this. So these two are the event which says an odd number of correct answers, which is how things are usually phrased when they ask you about a probability. They don't just enumerate a bunch of elements of a set. They'll ask you a question like, what's the probability of getting a 10 or higher, or getting an odd result, or something like that. And so if we look over here, we notice that this one here is the set which corresponds to the question, or to the set, an odd number of correct answers. And, if we go back to our definitions, we know that the sigma algebra has to include the complement of it in S. And so the complement of this set is actually the one right below it. And that would be the odd number of correct answers, the even number of correct answers. So, and if you add all these together, so all these 4 outcomes, 1, 2, 3, 4, you get basically the elements of S. So essentially what this sigma algebra is doing is allowing us to create a formal space in which we can define our events and for them to live and be happy in. Okay, so here's some examples with, suppose we're rolling 3 dice. Okay, so our sample space is the set of all triplets, D1, D2, D3, where the dice have values between 1 and 6. Okay, now in most of the cases that you're going to consider, the power set, the sigma algebra and the power set are going to be the same. So in this case, it is the same. There are cases where the sigma algebra could be smaller, but that's not something we're going to talk about. So when we set up an event, that event will be taken from the sigma algebra for S, and which is, in this case, is the power set and the set of all subsets of S. So any event E is in the sigma algebra, which is a subset of the power set of S. Again, there's a lot of stuff going on here, but really the main focus is we need a formal space to define events in. And since events are combinations of outcomes, then we need something that's a little bigger than just the sample space. And so that's why we have to resort to the power set, or a subset of the power set, which is bigger than, much bigger. Okay, so an example. 1. Remember, we've rolled 3 dice. Okay, here I should write the result of the sum is odd. So you would write that out as D1, D2, D3, such that there exists an n in the natural numbers, such that the sum is equal to 2n plus 1. That's the formal way of writing that. And then you could go and you could start to enumerate them, and here's a few elements of them. And then there's a lot more, because, there's a lot of ways of getting odd numbers. If you have one odd number and two evens, the result will be odd. If you have three odd numbers, the result will be odd. So all of those would be inside of this big set. And by definition, this thing will be contained within the power set, which in our case is the sigma algebra. So essentially the question, the event, the result of the sum is odd, is already enumerated somehow in this sigma algebra. And so really when we're kind of looking at the probability of it, we're just going to find it in this set. So and it would look a little different. Obviously it wouldn't be exactly the same as the other one because the other one was a little simpler, but you get the idea. In the second example, we have that the sum is greater than 10. So here we have all of the numbers where if you had a 1, a 6, the next number would have to be at least a 4, or else it would be equal to 10, which is not greater than 10. Or if you had a 1 and a 5, then the third number would have to be a 5, and you could mix that up. But essentially, you would wind up listing every single one of these elements, and that would wind up being a set, which is contained in that sigma algebra, which is essentially the power set for S. S being the dice setup that we have here. Okay, so really, so what's the use of these things? Like, why is it defined in such a way? Well, the first one is because we want to have probabilities that are equal to 0, okay? And the second one is, if I know that the probability of A happening is something, then I should know that that's equal to 1 minus the probability of it not happening, because something can either happen or it can't. There's nothing between those two. Okay? Now, for us to be able to apply like a probability function on these two things, they have to be defined. And this guarantees that they're defined because they tell you, because you're going to define the probability function on a sigma algebra, which will guarantee the existence of the complements. And that's why we've specifically written that into the definition. And the third, again, that has to do with just the nature of some of the models that we use for probability that allow for an infinite number of values. So I hope that this has been a reasonable explanation